Welcome to Deep Thinkers. Settle in. Let your shoulders drop away from your ears. Let the weight of the day loosen its grip on you, one finger at a time. And let the room around you soften into something dim and safe and quiet. There is nothing you need to do now. There is nowhere you need to be. Tonight we are going to travel a very long way down and a very long way back in time. And you do not have to stay awake for all of it. You are allowed to drift. You are allowed to sink. The story will keep going gently, whether you follow every word or let it dissolve into sleep, and that is exactly how it is meant to be heard. So let me begin where the story begins, which is beneath you. Not far beneath you, if you happen to be near the Mediterranean, but beneath the water, and then beneath the floor of the water, and then deeper still, under layers of mud and sand and the slow rain of everything that has ever died in that sea and settled down into the dark. Down there, hidden, is a wall of salt, not a vein of salt, not a seam of it, the kind a miner might chase with a lamp on his forehead. A wall, a body of salt so vast that the word wall almost embarrasses itself trying to hold it. In the deepest central basins of the Mediterranean, this salt reaches thicknesses of up to 2, even 3 kilometers. 2 miles in the old measure. Imagine standing at the bottom and looking up through solid mineral, and above your head there is more salt than there is air between the ground and the clouds on an ordinary afternoon. And it is not only thick, it is wide. It spreads out beneath the sea across an area you would need a map of a continent to draw. The total volume of it, when the geologists add it all together, comes to something on the order of 1 million cubic kilometers. 1 million cubic kilometers of salt buried under the seabed of a sea that people sail across every single day without the faintest idea it is there. Boats pass over it. Ferries between islands pass over it. Fishermen drop their nets above it and pull them up and never know that below the fish, below the mud, below the bones of older fish, there is a hidden colossus the size of a small country made of the mineral you keep in a little jar beside your stove. Sunseekers float on their backs on the surface, eyes closed, warm, weightless, and beneath them, kilometers down, sleeps the largest deposit of salt in this part of the world. They are floating on the evidence of something, and they do not know what. That is the first quiet thing I want you to carry into sleep tonight, that the ordinary, sunlit, postcard blue Mediterranean is lying on top of a secret. And the secret is enormous. And the secret is old. Because here is the question that a wall of salt like that forces you to ask. Where did it come from? Salt does not simply appear at the bottom of a sea. Salt like this much of it, layered and thick and pure, forms in only one way that we understand. It forms when seawater evaporates, when the water leaves and the minerals it was carrying stay behind. A shallow puddle of seawater drying in the sun will leave a white crust when it goes. That crust is the salt the water could no longer hold. And to make a wall of salt kilometers thick, you do not dry a puddle. You dry a sea. You dry an entire sea, and then you do it again, and again, and again, drying and drying, until 1 million cubic kilometers of dissolved mineral has been squeezed out of the water and stacked up on the floor like sediment, like snow that never melts. Which means that the wall of salt beneath the Mediterranean is telling us something almost impossible to believe. It is telling us that the Mediterranean once dried up, not a bay of it, not a corner, the whole sea, the great blue body of water that borders 3 continents, that cradled so much of human history on its shores that we think of as permanent and eternal and simply there. That sea once went away. It emptied. It vanished. And where the water had been, there was a desert of salt lying kilometers below the level of every other ocean on the face of the earth. And then, after a very long time in the dark, it came back. That is our story tonight. A sea that died and a flood that resurrected it. And the strange, wonderful thing, the thing that makes this more than a fairy tale, is that both events left their evidence behind, and the evidence is still here. The corpse of the sea is that buried salt. And the thing that brought it back, the flood, carved a scar into the rock that we can still find, still trace, still argue about. Because scientists do argue about it. There is a great deal about this that we know with real confidence, and there is a stubborn, fascinating core of it that nobody fully knows even now. And I will be honest with you all the way through about which is which, because the not knowing is not a flaw in this story. The not knowing is part of what makes it beautiful. So let us slow down and lay the ground properly, the way you smooth a sheet before you lie down on it. To understand how a whole sea could disappear, you first have to understand a strange fact about the Mediterranean itself. It is a fact that most people who swim in it never think about, and it is the key to everything that follows. The Mediterranean is what geologists call an evaporation basin. What that means, in plain and ordinary language, is this: the Mediterranean loses more water than it is given. The sun beats down on that wide, warm surface, day after day, year after year, and it lifts water off the sea and into the air as vapour, endlessly, evaporation, and the rivers that empty into the Mediterranean, the Nile, the Rhone, the Po, all of them together, do not bring in nearly enough fresh water to replace what the sun takes away. Think about that for a moment, slowly. If the only water going into the Mediterranean were the rain and the rivers, the sea would be losing a race it could never win. The sun would be drinking it faster than the rivers could pour. Left to itself, cut off, the Mediterranean would begin to shrink. Its level would fall. It would draw down like a bath with the plug pulled and only a trickle from the tap. So why doesn't it? Why is the Mediterranean full, right now, tonight, brimming and blue and lapping at all those familiar shores? Why is it a sea at all and not a shrinking salt pan? The answer is a single narrow doorway at its western end. A gap between the tip of Spain and the coast of Morocco, so narrow you can see across it on a clear day. The Strait of Gibraltar. Through that strait, water pours in from the Atlantic Ocean, a steady, patient, endless flow of ocean water coming in to top the Mediterranean back up. Everything the sun steals from the surface, the Atlantic quietly replaces through Gibraltar. That is the deal. That is the arrangement that keeps the Mediterranean alive. It is a nearly landlocked sea, held full by a thread of connection to the greater ocean beyond. And once you understand that, once you really feel it, a very unsettling thought arrives all on its own. Slowly, quietly, like a cold current under a warm one. What would happen if that doorway closed, if something were to shut the Strait of Gibraltar? If the Atlantic could no longer reach in and refill what the sun burned off? The arrangement would break. The generous replacement would stop. And the Mediterranean, cut off, would be left alone with the sun and its own losing arithmetic. The evaporation would go on, because the sun does not care about arrangements, but nothing would come in to replace what left, and the sea would begin to fall. That is not a fantasy. That is not a thing I am inventing to frighten you gently as you fall asleep. That is precisely what happened. Around 6 million years ago, that doorway closed, And the Mediterranean, deprived of the ocean, began the long, slow, terrible business of drying out. And that event, that closing, that drying, that vanishing, has a name. It is called the Messinian Salinity Crisis. Let me give you that name slowly, because we are going to be living inside it for the whole of tonight, and I would like it to feel like a familiar room by the time we are done. The Messinian Salinity Crisis. Messinian Salinity Crisis. 3 words that hold an entire Dead Sea between them. The middle word is the easy one. Salinity simply means saltiness, the saltiness of water. And crisis is the ordinary word we use for a turning point, an emergency, a moment when things could go one way or another and everything hangs on it. So a salinity crisis is, in the simplest telling, a crisis of saltiness. A time when the salt in the sea went wildly, catastrophically, out of its ordinary balance, which, as we will see, is exactly what it was. The water left, the salt stayed, and what remained behind grew saltier and saltier and saltier until it could hold no more, and the mineral began to fall out of it and pile up on the floor. A crisis of saltiness. Yes, that name is honest. But the first word, Messinian, is the one worth pausing over, because it carries a small human story of its own, and it will help you feel how long ago all of this really was. Geologists, you see, do not measure the deep past in ordinary years the way we count birthdays. The stretch of time they work in is so vast that plain years become useless. The way inches would be useless for measuring the distance to the moon, so they divide the history of the Earth into great named blocks, eras and periods and epochs, and smaller slices within those called ages or stages. And each of these carries a name, and the names come from places, from real spots on the map where the rocks of that particular time were first studied, first described, first understood. The Messinian is one of these stages. It is the very last age of the epoch called the Miocene, the final chapter, if you like, of a long book of Earth's history, running from about 7.25 million years ago down to about 5.33 million years ago. And its name comes from the city of Messina, on the northeastern tip of the island of Sicily, right where Sicily reaches toward the toe of Italy across a narrow strait. It was named after Messina by a geologist called Carl Meyer Eimar in the year 1867. Hold that in your mind for a moment. A man in the 1800s, more than a century and a half ago, looking at the layers of rock on and around Sicily and deciding that this particular slice of deep time deserved a name of its own and reaching for the name of the city on the shore. He could not have known, that man, what he was naming. He could not have known that the very slice of time he was labelling after a Sicilian city would turn out to hold one of the strangest catastrophes in the whole history of the Mediterranean. He was simply doing the patient, careful work of the geologist, sorting the layers, giving them names, building the calendar of the deep past, one stage at a time. But the name stuck, and it grew, and now, when we speak of the Messinian salinity crisis, we are reaching all the way back to a decision made by Carl Meyer Eimar in 1867 and forward through it to a Dead Sea, and it all hangs together on the name of a city you could sail into on a warm afternoon. And Sicily, as it happens, is not an accident in this story. Remember that name, Messina, and remember that island, because Sicily sits right at the heart of everything we are going to talk about. The salt is there, the flood scar is there. The evidence you can walk up to and touch with your own hand is there, on Sicily and near it. The island where the stage got its name is also the island where the vanished sea left some of its clearest fingerprints. But we are getting ahead of ourselves, and there is no hurry tonight. None at all. So let us fix the shape of it in time. The Messinian salinity crisis, the Great Drying, took place across a window running roughly from 5.96 million years ago to 5.33 million years ago. Say those numbers slowly to yourself, or don't, and just let the size of them wash over you. Nearly 6 million years ago it began. A little over 5 million years ago it ended. In between lay something on the order of 500,000 years, 500,000 years, of a sea in trouble. 500,000 years. That is longer than our whole species has existed. Modern humans, all of recorded history, all the pyramids and empires and songs, everything, would fit many times over inside the span during which the Mediterranean was drying and refilling and struggling with its salt. That is the scale we are drifting down into tonight. Not the scale of a lifetime, not the scale of a civilization, the scale of the earth itself, turning slowly in the dark. And I promised you honesty, so let me plant, right here at the start, the two great quiet mysteries that we will carry with us all the way down and all the way back up. Two questions that scientists still genuinely debate, still argue over in papers and at conferences, questions that do not yet have settled answers. I want you to hold them loosely, the way you might hold two smooth stones in your palm, turning them over now and then without needing to decide anything about them. They are the open doors of tonight's story, and we will walk toward them slowly. The first mystery is this. When the Mediterranean dried out, when the water fell away and the salt piled up, what was actually down there on that deep exposed floor? Was it a true desert? A baking, blinding, sun-hammered plain of salt and rock, cracked and dry and utterly waterless, lying more than a kilometer below the surface of every other ocean on the planet? A place like the lowest, hottest deserts we know today, but deeper and stranger than any of them. That is one picture, and it is a powerful one. But there is another. Perhaps the deep basin never went fully, truly dry. Perhaps instead of a bone-dry desert, there remained down in the deepest hollows a shrunken hidden lake, not a sea, but a heavy pool of water so laden with salt, so thick and dense and poisonous with dissolved mineral, that almost nothing could live in it. A brine lake sitting in the deep dark kilometers below the world. Desert or brine, a dry death or a drowned one. To this day, honestly, the debate is not fully closed. Two long-standing models sit side by side, and good scientists hold each of them. Keep that stone in your palm. Was it desert or was it brine? We will turn it over as we go. And the second mystery, the one that gives the whole story its strange and lovely ending, is about how the sea came back. Because it did come back. The Mediterranean is here, full tonight, so at some point the water returned. But how? Did it return slowly, gently, a gradual reconnection over many long ages, the Atlantic finding its way back in through some reopening gap, little by little, patiently refilling the basin the way it had drained, in slow motion over thousands upon thousands of years? Or did it come back all at once, in a single unimaginable event, a flood so sudden and so violent that it may have refilled an entire sea in a span of time you could almost measure against a human life? A slow reunion or a catastrophic instant? That, too, is genuinely disputed. There is a powerful and influential model for the violent version. We will come to it. And it is one of the most astonishing pieces of science I know, but it is a model, not a settled fact, and I will keep saying so, because the honesty is the point. Slow return or sudden flood. Turn that stone over too, and hold it gently. There, two mysteries, seeded and set aside. We will come back to them. We always come back, in this story. That is its nature. And there is a third small puzzle I want to open now as well, smaller than the other two, but delicious in its own way, a little thread to pull on later. It is this. If the Mediterranean dried out nearly 6 million years ago and refilled soon after, and everything that happened deep beneath what is now a deep sea, how on earth do we know any of it? How did anyone ever discover that the water we sail on today is sitting on the grave of a vanished one? You cannot see the buried salt from a boat. You cannot see it from the shore. It is kilometers down, under mud and water. So how did the secret ever get out? The answer to that involves a ship, a very particular ship with a strange name and a drill and the year 1970, and a crew of scientists who pulled something up from the deep floor of the Mediterranean that made absolutely no sense, until, slowly, it made all the sense in the world. That ship pulled up desert salt from the bottom of a deep sea. Minerals that can only form in the open air, in the drying sun, hauled up in a core of rock from far beneath the waves. And when the scientists on board looked at what they were holding, they understood, with a kind of vertigo, that they were holding proof that the sea beneath them had once not been a sea at all. But that story, too, will keep. Hold the thread. We will follow it back to that ship in good time. Now, before we go any further down into the dark, let me do a small and ordinary thing, and then we will return to the deep and the quiet and stay there. If you are enjoying drifting through this with me, if this slow kind of journey helps carry you towards sleep, I would love for you to subscribe to Deep Thinkers, so that these long, calm voyages into the strange corners of the earth keep finding their way to you on the nights you need them. And I am always genuinely curious where in the world you are listening from tonight. If you feel like it, later, when it will not disturb your rest, leave a note in the comments telling me where you are, which country, which city, which quiet room. It is a strange and lovely thing to imagine all of us scattered across the whole surface of the planet, lying in the dark and drifting off inside the same old story about a sea that vanished. So tell me where you are, whenever the mood takes you. But there is no rush. Nothing tonight has any rush in it at all. Now let us go back down. I want you to try, gently, to picture the thing we are really talking about. Not the map of it, not the diagram, the place itself. Because it is easy to say the words a whole sea dried up, and it is much harder and much more worth doing to actually stand inside that idea for a moment before sleep takes you. So imagine that you could take away the water. All of it. Imagine that the blue skin of the Mediterranean were peeled back, drained away, and you were left looking at the bare floor where the sea had been. It is not a smooth, flat pan. It is a landscape, a real landscape, with deep basins and rises and slopes, hollows plunging down into the central deeps and high ground between them. And now imagine that the sun is on it, that there is no water at all, and the sun is beating down on this exposed floor day after day, century after century, and there is nothing to reflect it, nothing to cool it, nothing but rock and salt and glare. And this floor is not at sea level. That is the part that makes the head spin, softly. This floor lies far, far below the level of the world's other oceans, well over a kilometer down, in the deep central parts, something like 1.5 kilometers below the surface of the Atlantic beyond Gibraltar. So if you were standing on that dry floor, and you could somehow look toward Spain and Morocco, toward that closed western doorway, the ocean on the other side of it would be up above you, higher than your head, higher than the highest hills you could see. A whole ocean held back, sitting more than a kilometer above the ground you were standing on. That is the vertigo of a lost base level, and we will feel it again later when we talk about the rivers. Because the rivers felt it too, and they responded in a way that left scars beneath modern cities. But for now, just hold the strangeness of it. A seafloor turned into the lowest, hottest, saltiest place on the planet, with the rest of the ocean towering silently above and beyond the sealed western gate. What did the sun do to that place over the long 500,000 years of the crisis? It did what the sun always does to trapped seawater, only on a scale almost beyond imagining. It dried it. And as the water left, the salt it had been carrying had nowhere to go but down, onto the floor, layer by patient layer. This is how you build a wall of salt kilometers thick. Not in a single drying, but in a long, repeated cyclical process, the sea drawing down and the minerals settling out, over and over, through cycle after cycle, until the deep basins had accumulated that colossal buried body we started with tonight, up to 2 or 3 kilometers thick. 1,000,000 cubic kilometers in all. The salt giant, sleeping beneath the modern seabed, exactly where it settled all those millions of years ago. And here is a thing to marvel at quietly, before we close this first part of the descent. That salt is still there. It never left. When the sea came back, however it came back, slow or sudden, it did not wash the salt away. It simply covered it. It laid itself back down on top of the salt, and the mud and the sediment of the ages settled over both. And there it has stayed ever since, the giant beneath the seabed, the buried remains of the sea that dried. So that when you float on the Mediterranean today, you are not floating above nothing. You are floating above a memory made of mineral. You are floating on the evidence. The corpse of the old sea is right there, under you, patient and enormous and still, and more than that, and this is where it stops being a story about somewhere far away and becomes a story you could reach out and put your hand on. In a few places on Earth, the salt of that vanished sea is not buried at all anymore. In a few places, the slow shoving of the continents, the same restless movement of the Earth's crust that closed the Western Gate in the first place, has since lifted some of those old evaporate layers up out of the deep, up above the water, up onto dry land. So there are places you can go, on Sicily, in Spain and elsewhere, where you can walk right up to the salt of the Messinian, the actual mineral that fell out of the dying sea nearly 6 million years ago, and lay your palm against it. The salt of a sea that no longer exists, that died and was reborn, sitting there in the sunlight where anyone can touch it. We will go to those places later, and I will tell you their names, and about the strange bands and rhythms written into that salt like the rings of a tree. But not yet. For now, simply know that it is there, and touchable, and real. So that is where we stand, as the first part of our long descent comes to its resting place. We have a sea that we now know once vanished. We have the reason it could vanish, a near landlocked evaporation basin, losing more to the sun than its rivers could ever give, kept alive only by the Atlantic reaching in through the single narrow doorway of Gibraltar. We have the name for the catastrophe, the Messinian salinity crisis, reaching back through the stage that Karl Mayer Aymar named after the Sicilian city of Messina in 1867, and forward across that vast 500,000-year window from about 5.96 to 5.33 million years ago. We have the buried salt giant itself, up to 2 or 3 kilometers thick. 1,000,000 cubic kilometers of it sleeping beneath the seabed we sail across without a thought. And we have our 3 open doors, our stones to turn over in the dark. Was the deep floor a true desert or a hidden brine? Did the sea return in a slow reunion or a violent instant? And how, in the end, did anyone ever find out any of it from a ship in 1970 that pulled desert salt up out of the deep? But we have not yet asked the first real question in the sequence. We have said that the doorway closed. We have not yet asked how. What was it, exactly, that reached across the narrow gap between Spain and Morocco and shut the Atlantic out? What sealed the Western Gate and left the Mediterranean alone with the sun? It was not a hand. It was not a wall built in a day. It was something far slower and far larger, something that had been moving for millions of years and is still moving under our feet right now. Tonight. Too slowly to feel. It was the continents themselves. And that is where we will go next, down into the story of how Africa pressed northward into Europe, and how that vast, patient, grinding collision closed not 1 but 2 ancient corridors that once let the ocean in and pulled the plug on a sea. But that current is for the next stretch of our journey, and there is no need to reach for it now. For now, just stay here a while, at the edge of the vanished sea, with the sun on the salt and the ocean towering silently beyond the closed gate, and let yourself go a little heavier, a little softer, a little further down. Africa and Europe have been pressing toward each other for longer than the Mediterranean has existed. That is the first thing to understand, and it is a thing the body resists. Not because it is complicated, but because the timescales involved refuse to fit inside any unit of time the human nervous system knows how to feel. We can say the words, 50 million years, 100 million years. The words are perfectly pronounceable, but they do not land as felt duration. They land as astronomy, as something that happens in another register of reality, the way we say the distance to a distant galaxy and mean, in practical terms, nothing at all. And yet, the collision is real. The seam is real. If you stand in the right places, in the folded limestone ridges of the Atlas Mountains in Morocco, or in the crumpled ranges of southern Spain, or in the great arcing curve of the Alps curling east across Switzerland and into the Balkans, you are standing on the wreckage of that collision. The rock beneath your feet was squeezed and lifted and buckled by 2 land masses grinding slowly into each other, and the reason you are standing on a ridge instead of a seafloor is that Africa was pushing northward, nudging its northern rim into the soft underside of Europe, and the crust had nowhere to go but up. This is the context for everything that follows. The tectonic convergence of Africa and Eurasia did not start at the Miocene. It did not start with the Messinian. It had been happening for ages before the Mediterranean we know had formed, and it continues now, invisibly, tonight, at rates of a few centimeters a year, too slow for any human life to perceive as motion, but fast enough over millions of years to move mountains. What changed in the late Miocene was a particular consequence of that convergence in a particular place. Not the full collision of the continents, but a narrowing, a tightening, a slow geological squeezing of the gaps. Because in the period before the Messinian salinity crisis, the Mediterranean was not isolated in the way it is now. It was connected to the Atlantic not through one narrow bottleneck, but through 2 separate openings, both of them wider and more generous than the modern Strait of Gibraltar. One of those openings lay through what is now southern Spain, a broad, low-lying seaway threading through the landscape of Andalusia through the Betic Basin, connecting the Atlantic coast to the west with the open Mediterranean to the east. Geologists call it the Betic Corridor. You can stand on land there today, on the dry plains and low ridges of southeastern Spain, and know that you are standing in water that once flowed freely between the Atlantic Ocean and the ancient sea. The corridor was real, and it was open, and for a long time the ocean used it. The other opening lay across the water on the opposite side of the gap. Through what is now northern Morocco, a second seaway passed, the Rifian Corridor, named for the Rif Mountains that today occupy that terrain. Like the Betic Corridor to the north, it was once a maritime passage, a channel of open ocean connecting the Atlantic to the Mediterranean and ensuring that inflow from the world ocean could replenish what evaporation was always drawing away. Two doors, held open by geography, keeping the sea alive. And then, slowly, both doors closed. The Betic Corridor was the first to shallow and narrow and finally shut, as the tectonic pressures lifted the land that had been its bed, as sediment filled what water had carved, as the sea retreated from the inland plain and left behind a landscape of hills and dry basins. This happened gradually through the later Miocene, not in a single moment, but in a long fading, a diminishment of flow. The Atlantic water that had passed freely through southern Spain found itself pressed through a narrower and narrower channel, shallowing over a rising threshold until the threshold rose above the water and the connection ended. Then the Rifian Corridor, to the south. The same convergence, the same slow lifting of the land, the same narrowing of the passage. By some time around 5.96 million years ago, around the beginning of what we now call the Messinian salinity crisis, both of those openings had been reduced to nothing. The land had closed over them. Africa's northward press had sealed them, not dramatically, not in a single seismic event, but in the patient way that continents do everything, one imperceptible adjustment at a time, over thousands and hundreds of thousands of years, until one day the water that had always flowed freely simply could not find its way through anymore. The Strait of Gibraltar, as we sail through it today, is not the same opening. Gibraltar, in the form we know it, did not exist as an open strait during the Messinian. There was land where the water now moves. And so when the Betic and Rifian corridors closed, the Mediterranean did not simply lose its main connection and retain a secondary one. It lost its connection to the Atlantic almost entirely. The great replenishing flow, the Atlantic water that had always compensated for evaporation, slowed to nearly nothing, and then to nothing, and then the sea was alone. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. Consider for a moment what that means for a body of water like the Mediterranean. It is not a balanced system. It never has been. The rivers that empty into it, the Nile from the south, the Rhone from the north, the Ebro and the Tiber and the Po and dozens of others, bring fresh water, but not enough. The evaporation over the warm surface of the Mediterranean takes far more water into the air than all those rivers together can return. Under normal conditions, under the conditions of the last several million years since the Atlantic reconnected, This deficit is made good by the inflow through the Strait of Gibraltar. Dense, saline Mediterranean water sinks and flows out at depth, and lighter Atlantic water flows in at the surface to replace it, and the system balances. The sea stays full. The salt stays diluted. Take that inflow away, and the arithmetic becomes merciless. The Mediterranean basin is a large evaporation engine, and it had been running for a very long time. Cut off from replenishment, it simply began to empty. Not overnight. Not in a year. The sea is immense, and its volume is enormous, and even with evaporation exceeding inflow. The drawdown would have been gradual by any human standard of time. But the sea has no human standard of time to keep. It does not care about urgency or patience. It simply continues to evaporate, year after year, decade after decade, century after century, and the water that leaves as vapour does not come back as rain in any quantity sufficient to matter. And so the level fell. Slowly at first, perceptibly perhaps only in the way that tide marks rise and fall on a beach, but over geological time the decline was inexorable. The coastlines retreated, the shallow margins, the continental shelves and the gentle slopes that had once been under water dried and baked and became land. The sea surface fell tens of meters, and then hundreds, and then more. The deep central basins, the western basin between Spain and the Italian peninsula, the eastern basin stretching toward the Levant, lay below the retreating surface, growing more isolated, more concentrated, as the water column above them diminished. Now the chemistry began to change, because when water evaporates, it takes the water with it and leaves everything dissolved in the water behind. The sea does not evaporate in a simple way. It does not produce fresh water and leave a uniform concentrated brine. As salinity increases, the dissolved minerals in seawater begin to precipitate out in sequence, settling to the bottom in a predictable layered order that geochemists understand well because they have watched it happen in modern salt-forming environments. The first minerals to fall out were the carbonates, calcium carbonate, the same material that makes limestone and chalk, settling in a thin layer on the drying floor. Then, as concentration continued and the water grew more saline than any normal ocean, the gypsum began to precipitate. Calcium sulfate, a soft, pale mineral that forms in crystals and massive layered beds, the kind of material found today in desert playa lakes and in salt flats, where seawater is deliberately evaporated in commercial saltworks. Gypsum falling slowly through increasingly salty water, accumulating in beds on the deepening floor of a dying sea. Then anhydrite, calcium sulfate without the water molecules that gypsum retains, forming under the pressure and heat of burial, converting from gypsum as the layers deepened. And then halite, rock salt. The ordinary familiar substance, the thing that sits in a cellar in a ceramic bowl or in a mine cut through mountains, falling now in enormous quantities from a hypersaline sea that had long since exceeded any salinity the normal ocean approaches. The salt that flavors our food and preserves our meat, and that the human body regulates with exquisite biochemical care, falling layer after layer in a dying Mediterranean basin, in quantities almost too large to imagine. And then, finally, the most soluble salts of all. The potash salts, the bittern salts, the materials that precipitate last from seawater because they are the most reluctant to leave solution, the ones that require the greatest concentration before they will abandon the liquid and join the growing accumulation on the floor. These are the last layers in the sequence, the top of the evaporate column, and their presence in a rock record tells a geochemist that the water that produced them was not merely salty, but extraordinarily concentrated, that very little water was left, that the evaporation had proceeded nearly to its logical end. This layered sequence, carbonates, gypsum, anhydrite, halite, potash salts, is the stratigraphy of a dying sea. Each layer is a chapter in the desiccation, a record of how concentrated the remaining water became before the next mineral was forced out of solution. Together they constitute what geologists call the salt giant, though they name it more precisely as the Messinian evaporate sequence, a body of rock that formed from the remains of a sea, and that now lies buried beneath the modern Mediterranean seafloor in thicknesses of up to 2 or 3 kilometers in the deepest central basins, with a total volume on the order of 1 million cubic kilometers. 1 million cubic kilometers. A body of salt the size of a small continent, lying in the dark beneath the water you cross on ferries between Barcelona and Palma, between Genoa and Tunis, between Piraeus and Heraklion. And while the salt was accumulating on the floor of the western and central basins, the sea continued to fall. By the time the evaporate sequence was well advanced, the surface of the remaining water, or rather the surface of the remaining hypersaline brine, because calling it water at that point is a courtesy, lay well over a kilometer below the level of the world ocean outside. More than that, by many estimates. The figures that geologists have arrived at through careful modelling of the sedimentary record suggest a drawdown on the order of 1.5 kilometres, perhaps more in the deepest parts. 1,500 metres of missing sea surface. The floor of the basin, where the salt was accumulating, lay kilometres below the normal ocean surface, kilometres below sea level as the rest of the world understood it. Picture what that means in terms of the landscape. Stand at the edge of the closed gate, somewhere on the hills of what would become Gibraltar, looking east. The land drops away on the Mediterranean side, and it keeps dropping. Not to a sea surface a few meters below you, as you might expect standing on a coastal cliff, but to a surface hundreds of meters below, then a kilometer below, the air thickening slightly as it descends into that tremendous depression. Below that surface, the floor lies lower still, 2 kilometers, 3 kilometers below where the outside ocean stands. The surrounding landscape, the mountains of northern Africa, the ranges of southern Europe, rises steeply from the edge of this vast sunken basin, and the basin itself sits in its depression like the deepest place on earth, which in one sense it was. At the floor, in the deepest and driest periods of the crisis, conditions would have been something like the environments we know today from the lowest places on the modern land surface. The Danakil Depression in northeastern Ethiopia, one of the hottest and most inhospitable places on Earth, sits about 150 meters below sea level. Death Valley in California drops to about 86 meters below sea level. These are the places that come to mind when we want to imagine what life is like at the very bottom of the world's depressions, the blinding heat, the crystalline salt flats, the silence, the sense of being in a place the rest of the world has forgotten about. The deep Mediterranean basin, at the height of the Messinian salinity crisis, would have lain not 150 meters, but perhaps 1.5 kilometers below the surface of the surrounding ocean. The air pressure at the bottom of that basin would have been noticeably higher than anywhere on the modern land surface. The temperature, in the absence of any ameliorating body of water, would have been extreme. The sun, already intense at those latitudes, would have beaten down on salt and rock without the moderation of any significant humidity, except for whatever evaporated from the remaining hypersaline pool or pools at the very bottom of the depression. Whether those pools were truly gone, whether the deepest floor was a genuine desert, hot and cracked and bone-dry, or whether a deep, dense, hypersaline brine persisted in the lowest basins, even at the nadir of the crisis, is one of the questions that remains honestly open. Two models have long coexisted in the scientific literature. In one, the deep basin dried completely, or nearly so, a true desiccated desert floor, a barren salt plain without standing water, swept by hot winds and baking under the Miocene sun. In the other, the basins retained a deep layer of brine, too dense and too hot and too concentrated to support normal marine life, too extreme to call a sea in any meaningful sense, but nevertheless liquid, nevertheless present. The evidence for both models exists in the geological record, and researchers have argued the case back and forth for decades. We will not resolve it tonight. And that is not a failure, that is the honest state of the knowledge, and there is something right about carrying an unresolved question into sleep rather than a false certainty. What is not in dispute is this: the chemistry of the basin changed to something entirely unlike normal seawater, and the normal marine life that had inhabited the Mediterranean before the crisis, the fish, the mollusks, the corals, the plankton, could not survive in it, or at least not in the hypersaline portions. A sea that had been a living system, a body of interconnected ecosystems stretching from the Strait of Gibraltar to the eastern Levant, became something else, something inhospitable. Something that had crossed a boundary no biological system could easily follow it across. And meanwhile, something strange was happening at the edges. At the margins of this vast, desiccated or hypersaline basin, where the rivers of the surrounding continents met the fallen surface, the geography was rewriting itself in ways that would leave permanent marks. Marks that millions of years later would become some of the first clues pointing toward the crisis itself. A river, any river, cuts its channel down toward the sea. This is what rivers do. They erode their beds and their banks, and they carry the material downstream, always working toward what geologists call base level. The level of the body of water into which they empty, the surface that defines the lowest point the river can, in principle, reach. A river emptying into the Atlantic carves its channel down toward Atlantic sea level. A river emptying into the Mediterranean carved its channel down toward the Mediterranean's surface. But what happens when the Mediterranean's surface falls? When the sea into which a river empties drops not a meter or 10 meters, but hundreds and then 1,000 and more? The river follows it. It has to. With the base level of its receiving basin dropping away beneath it, the river suddenly finds itself elevated above the destination it has always been moving toward. So it cuts. Downward, aggressively, energetically, it erodes its bed with renewed force, because the gradient between where it is and where it needs to go has steepened dramatically, and steep gradients accelerate erosion. The river carves its channel down toward the fallen surface of the dying sea, cutting through whatever rock lies beneath it, cutting canyons where there had been gentle valleys, cutting gorges hundreds of meters deep in pursuit of a sea level that kept retreating. The Nile did this. The great river, which had been flowing north toward the Mediterranean long before the Messinian, found its base level collapsing as the sea drew down, and it cut. The ancestral Nile, what geologists call the Nile, carved a canyon through the rock of northeastern Africa as it chased the retreating sea surface, a gorge that extended inland for a very great distance, deepening as it went, reaching depths of hundreds of meters below what was then, and what is now, the surface of the delta plain. Deep beneath the modern city of Cairo, beneath the streets and the foundations and the deep bones of a city that would not exist for another 5.5 million years, that ancient canyon still exists. It is filled now, filled with sediment deposited when the sea returned and the river built its delta up from nothing, filled with the accumulated material of millions of years of geological time. But the shape of it, the hollow cut into the rock by a river chasing a vanished sea, is still there. Geophysical surveys have traced its outlines, mapped its depth, followed its course through the subsurface of one of the oldest inhabited landscapes on Earth. The canyon beneath Cairo is in some sense a wound, a trace of the violence done to the landscape when the sea abandoned it. The Nile cut that gorge in pursuit of a Mediterranean surface that had fallen beyond anything it had ever known, and when the sea returned, the canyon was buried and the wound was covered over, and above it the delta spread and the civilization grew. And the canyon slept in the rock beneath everything, holding the memory of the crisis in its shape. The Rhone did something similar. The great French river, draining the interior of Europe, cutting south through limestone and through the ancient rocks of the massif central, met the same collapsing base level and cut the same deep answer into the landscape of what would become France. The ancestral Rhone Canyon, buried now, like the Nile Canyon, beneath the accumulated sediment of millions of years, descends to depths far below the modern river's bed, far below the Mediterranean's current level, far below anything the modern geography could explain without the context of the crisis. Boreholes drilled for geological surveys and for engineering projects have penetrated the canyon's fill and found it there, ancient sediment where solid rock should be. The signature of a void that the river cut and the returning sea then filled. These rivers were among the first witnesses. Long before anyone thought to drill the deep Mediterranean seafloor and pull up strange minerals from the depths, the buried canyons were there, waiting. Geologists who mapped the deep structure of the Nile Delta and of the Rhone Valley found that the rock beneath the sediment had been carved far too deeply to be explained by any process operating under current sea levels. The canyons were anomalies. They were clues without a crime scene, patterns that demanded an explanation that hadn't yet been proposed. What had the base level of the Mediterranean been to carve gorges that deep? How far had the sea fallen? The questions hung in the air, in the geological literature, in conference rooms, in the margins of papers about Mediterranean stratigraphy, for years, without a satisfying answer. The buried canyons were real, the depths were real. What could have produced them? The answer was sleeping beneath the seafloor, 2 or 3 kilometers down, compressed and quiet and undisturbed, waiting for a drill to find it. But that is the story of another part of this journey, the story of a ship that appeared in the Mediterranean in 1970 and pulled the past up out of the dark. For now, stay with the rivers. The Rhone cutting through southern France, the Ionile cutting through northeastern Africa, and the other rivers that must have done the same, all of them responding to the same signal, all of them cutting down toward a surface that had departed, all of them carving the geological evidence of a sea's disappearance into the landscapes they passed through. The evidence was written in rock. It waited in the dark. It would not be read for millions of years. Above these deepening canyons, the landscape of the basin margins was changing too. The shoreline, such as it was, had retreated far from where it had once been. Lands that had been shallow seafloor were now exposed to the air. Plains that had once lain under gentle, warm Mediterranean water now baked under a sun that had no water to reflect. And the basin as a whole, with its deepening floor of accumulated salt and its falling surface, was becoming something truly extreme. Something that, in the depth of the crisis, would have had no close modern analogue anywhere on the surface of the earth. The Danakil Depression, at 150 meters below sea level, gives some impression of what extreme terrestrial heat and salt and hyperaridity can look like. Sulphurous springs and acid pools and salt flats that gleam white under a sky too bright to look at directly. Death Valley, in its August heat, with its salt pans and its cracked mud and its silence that is not peaceful but hostile, gives another impression. Take those images and pull the floor a further kilometer and more below the level of the surrounding sea. Increase the atmospheric pressure at the bottom of the basin. Concentrate the remaining brine beyond anything the Danakil or Death Valley contain, and you begin to approach what the deep Mediterranean may have been. Not may have been. Was. In some form. The evaporites are the proof, the gypsum and halite and bitten salts now buried under the modern seabed are the chemical residue of what the water became before it was gone. The question that remains open is only the degree. How dry did the floor become? How complete was the evaporation at the deepest point? The salt says, very far. The full answer is still being worked out. And through all of it, through the decades of evaporation, through the layering of carbonates and gypsum and halite on the deepening floor, through the cutting of the buried canyons and the retreat of the shore, the basin was accumulating a debt. A chemical debt, a structural debt, a gravitational debt. The salt that precipitated from the evaporating water was salt that had originally come from the ocean. The ocean had loaned it to the Mediterranean, which had carried it for millions of years, dissolved in seawater, and now the Mediterranean was not returning it. The salt was not going back to the Atlantic. It was sitting on the floor of the basin, building up in layers, being buried under its own weight, compacting and drying and becoming something geological rather than something aqueous. 1 million cubic kilometers of salt drawn from the world ocean over the course of the crisis, gone from the ocean's chemistry, removed from the global marine system and locked in a basin that had closed its doors. And this removal left a fingerprint in the chemistry of every sea on the planet, a fingerprint subtle enough that it took very careful scientific work to detect, but real, measurable, written into the geochemical record of the Miocene Ocean. We will come to that fingerprint in its proper place in the story when the full scale of the salt giant has settled in and the numbers have had time to become imaginable rather than merely large. For now, hold the thought loosely that what happened in the Mediterranean was not a local event, that the closing of 2 narrow corridors in what would become Spain and Morocco sent ripples outward through the chemistry of the whole world ocean, that the Mediterranean's disappearance was a planetary event in disguise, hidden behind a sea-sized container, hidden behind a quantity of salt that by any normal measure of the world is inconceivable. The salt lay on the floor in the dark. The rivers cut their canyons. The basin deepened into something that had no precedent in the living world. And outside, beyond the closed gate at Gibraltar, the Atlantic moved as it always had, knowing nothing of the catastrophe on the other side. Its waters rolling and circulating and carrying their normal cargo of dissolved minerals and dissolved life. The sea that had vanished was not dead in the way that a fire goes out or a light is switched off. It was more like something that withdraws, that recedes into itself, that becomes more concentrated and more extreme and more remote from everything that surrounded it, until it was something other than what it had been. Still, a body of liquid, in some form, perhaps, still accumulating salt and chemistry and geological record. But no longer a sea in the sense that the word carried before the crisis, no longer open, no longer exchanging freely with the ocean, no longer a living system in anything resembling its former sense. The withdrawal took time, hundreds of thousands of years at least, maybe longer. It did not happen in a year or a century. It happened in the patient, grinding, inexorable way that geology always works, slowly enough that nothing watching from the shore would have perceived it as a single event, but fast enough on a geological clock to count as a catastrophe. And when it was over, or nearly over, when the basin had reached the extreme of its desiccation, and the salt was thick, and the canyons were deep, and the surface of the remaining brine lay kilometers below the sea outside, a different kind of waiting began. The waiting for the door to open again. And something else was happening in that intervening time. A stranger, quieter chapter in the story of the dying sea. Not the baking desert phase, not the deep salt plains, but something that came later and that the geological record preserves in its own distinctive way. A transitional phase, a twilight between the arid extreme and the return of normal ocean conditions, something that has been given its own name. And that tells a story not of absence, but of a different kind of presence, a brackish, alien presence. A quasi-sea fed not from the Atlantic, but from the east, from a body of water connected to an entirely different ocean system, populated by organisms suited to neither saltwater nor freshwater, but to something in between. The Lago Mare, the Lake Sea. But that is where the next passage of this journey begins, and there is no need to reach for it yet. Let it wait in the dark where it has always been, patient as salt, patient as geology, patient as a sea that has not yet found its way back to itself. For now, stay with the rivers cutting down through the rock beneath France and Egypt, chasing a sea they could not reach. Stay with the salt lying in layers in the dark of the deep basin. Stay with the picture of two corridors, the Betic through Spain, the Rifian through Morocco, slowly closing under the weight of Africa's northward press, and the Mediterranean left alone with its own chemistry and the indifferent Miocene sun. The deep floor lies there in the silence, 2 or 3 kilometers of salt piled up over time, waiting. The canyon of the ancestral Nile lies beneath the future site of Cairo, waiting. The canyon of the ancestral Rhone lies beneath the alluvial plain of southern France, waiting. And the closed gate at the western end of the basin holds against the Atlantic, which has been waiting on the other side, perhaps without knowing it was waiting, if we can extend the metaphor, which we do with the full knowledge that geology has no intentions, only forces. And let your own mind rest, if it wants to, in that waiting space. There is no urgency here. There is no arrival expected tonight. The sea will return in its own geological moment, which from our perspective lies several million years in the past, and which will not be rushed by anything we do or think or feel. Let the layers of salt settle into their proper thickness. Let the rivers keep their slow work in the rock. Let the sense of that tremendous sunken plain, kilometers below the surrounding world, settle into the body as a physical sensation, the depth of it, the silence of it, the strange completeness of a basin that has drawn into itself. The story has more to give. It will be here moving at exactly this pace for as long as you want to stay inside it. In the year 1970, a ship called the Glomar Challenger was moving slowly across the Mediterranean, lowering a drill string through water several kilometers deep. The Glomar Challenger was not a large or beautiful vessel in the way that the great ocean liners of an earlier century were beautiful. It was a working ship, flat-decked, industrial in its proportions, purpose-built for a kind of inquiry that had not existed before. The systematic drilling of the deep ocean floor to recover cores of what lay beneath it. And what the drill recovered from the Mediterranean floor on that particular voyage was something that nobody had expected to find. The voyage was part of the Deep-Sea Drilling Project, a multinational scientific program that was then only a few years old, and the Mediterranean leg was designated Leg 13. The scientists on board included Kenneth J. Hatches, a sedimentologist of Chinese-Swiss background, who had a reputation for combining rigorous geological thinking with a willingness to follow the evidence wherever it led, even when that evidence pointed somewhere that seemed impossible. William B.F. Ryan was also aboard, an American oceanographer, and Maria Biancasita, an Italian micropaleontologist whose specialty was the tiny fossilized shells of single-celled organisms called foraminifera, creatures so small that their remains could pass through the eye of a needle, but whose presence or absence in a sediment core tells you almost everything you need to know about the water conditions that existed when those sediments were laid down. The drill went down through the water column and into the seabed, and the cores came up in sections, each one a cylinder of material pulled from depths that no human hand had touched before. And what those cores contained, when the scientists opened them on deck and examined them under the pale Mediterranean light, was not what anyone had predicted. They found gypsum. Gypsum is a mineral, calcium sulfate, and it is one of the evaporate minerals, a mineral that forms not in deep open water, but in water that is evaporating. In water that is growing so concentrated with dissolved material that the material precipitates out of solution and settles to the bottom as solid crystals. You see it in the margins of drying lakes, in the white-crusted flats of desert basins, in places where the sun is doing visible work on standing water and the water is losing its battle against the heat. You do not find it at the bottom of a deep, open, actively circulating sea. You should not find it at the bottom of the Mediterranean, which is, by any modern measure, a deep basin, reaching over 3 kilometers in its deepest trenches, and which is constantly receiving new water from the Atlantic through the Strait of Gibraltar. And yet there it was, gypsum and anhydrite being gypsum's dehydrated cousin, even more telling as an indicator of extreme evaporative conditions, pulled up from beneath what the instruments insisted was thousands of meters of seawater. Pulled up from a place where, by all reasoning, evaporates had no business existing. H. later described the moment of recognition with a scientist's care for what can and cannot be claimed. But the implication of those cores was not subtle. The minerals in their hands formed in shallow, evaporating water. The only way such minerals could exist beneath the deep floor of the Mediterranean was if the deep floor of the Mediterranean had once not been deep water at all. If at some point in the past those basins had been exposed to the air, or nearly so, if the water had retreated, concentrated, and finally done what water does when it is left too long under an unrelenting sun. It had precipitated its contents and left them behind as rock. The Mediterranean had dried. Not completely, perhaps, not in the way that a glass of water left on a summer windowsill dries. The basin is enormous, and the question of what exactly happened in those deepest floors, whether they became a true desert, sun-cracked and salt-white, or whether they retained a deep and impossibly saline brine lake far below the level of the world's oceans, that question was not answered by the cause on the Glomar Challenger's deck. And it is still not fully answered now. But the cause were unambiguous about one thing. Evaporation had happened here, on a scale that geologists had no framework for before this moment. The Mediterranean had drawn down. It had concentrated, and the evidence of that concentration, pressed now into solid mineral layers, was sitting in cylinders of drilled sediment on the deck of a research vessel in the middle of a sea that had, by all appearances, no idea any of this had ever occurred. Maria Biancasita's contribution was equally important, though it came from a different direction. In the cause, at the boundary where the evaporate minerals gave way to normal deep-sea sediment above them, the sediment of the Pliocene, the epoch that followed the Messinian, she found an abrupt change in the foraminifera assemblage. Below the boundary, the wrong creatures, sparse, stress-tolerant organisms adapted to abnormal, hypersaline or near-absent marine conditions. Above it, suddenly and completely, the normal rich community of open ocean foraminifera, the kinds that live in well-mixed, normally saline, well-oxygenated seawater. The change was sharp, not gradual, not a slow transition. Something had ended abruptly, and something had begun. Let that finding settle for a moment, because it is one of those scientific results that contains a whole geological history inside it, compressed into a thin line drawn through a sediment core. Below the line, crisis; above the line, normality; and in between, almost nothing, a horizon so sharp you could put a fingernail on it and say, "Here." Here is where the sea came back. The Glomar Challenger's Mediterranean cause announced to the geological world that the Messinian salinity crisis was real. Not a legend, not an extrapolation. Real, solid, chemical, mineralogical. The salt was there. It had always been there, buried beneath the seabed, patient as only geology can be patient, and now it had been found. But finding it raised a second question, which is in some ways more interesting than the first, because it reaches deeper into the nature of time. The evaporites were there, the crisis had happened, but when, exactly? And over how long? And was it one event, or many? Was the drying sudden or gradual? Was the return sudden or gradual? The cores themselves could not answer these questions with the precision that the questions deserved. For that, a different kind of reading was required. Not the reading of chemistry, but the reading of rhythm. Within the evaporate layers, and particularly within the gypsum, which is slightly more tractable as a recording medium than halite or anhydrite. Geologists examining cores and exposed outcrops eventually noticed something remarkable. The layers were banded, not randomly, not chaotically, but in a repeating cyclical pattern, thick layers alternating with thin, light with dark, rich with lean, in a rhythm that, once someone thought to measure it carefully, matched something they recognized from an entirely different context. The Milankovitch cycles. Milutin Milankovitch was a Serbian mathematician and astronomer who spent much of the early 20th century calculating, by hand, the variations in the geometry of Earth's orbit around the Sun, the way the orbit stretches and contracts over long periods, the way Earth's axial tilt wobbles like a spinning top, and the way the direction of that tilt slowly revolves over time. This last cycle, the precession of the equinoxes, completes one full revolution in roughly 21,000 years. And precession matters because it determines which hemisphere of Earth is tilted toward the Sun when Earth is at its closest approach to the Sun in its orbit, which in turn matters for how much solar energy reaches different parts of the planet at different times, which in turn matters for how wet or dry, how warm or cool the climate is at any given place in any given millennium. Milankovitch predicted that these orbital rhythms should be detectable in the geological record as repeating climate cycles, and eventually, in many places and in many types of sediment, they were found. But to find them in the gypsum of the Messinian evaporates was something particular, something almost startling in its elegance. Because what it meant was this: the Mediterranean had not dried all at once and simply stayed dry. The drying had been paced by the sky, by the slow rhythmic variations in how much sunlight reached the Mediterranean basin over cycles of roughly 21,000 years, the precession cycle, driven by the gradual wobble of Earth's axis. During the drier, hotter phases of those cycles, evaporation intensified and the basin concentrated its salts more rapidly. During the wetter phases, rivers brought more fresh water in and precipitation of salts slowed. And this rhythm was written, layer by layer, into the mineral record with a fidelity that geologists found extraordinary. It is called astronomical tuning, this method of correlating the rhythms in a geological record to the calculated rhythms of Earth's orbital mechanics. And it is one of the stranger achievements of modern geology, the use of planetary-scale celestial physics to calibrate the clock of a sedimentary record. When the gypsum bands in a Messinian outcrop can be matched to the precession cycle with enough confidence, they can be assigned absolute ages to a precision that is sometimes better than 100,000 years for events that happened nearly 6 million years ago. 6 million years, and we can read the clock to within a human lifetime's margin. One of the places where this clockwork is most tangible is not on the seafloor, and not in a drill core, but in a salt mine in the interior of Sicily, in the hills south of Agrigento, in a place called Rhone. The Rhone salt mine has been worked commercially for decades, and if you were to walk its underground corridors, which are carved directly through the ancient evaporate deposit, you would find yourself inside what is effectively a geological record made physical. The walls around you are not uniform, they are striped. Thick bands and thin bands, light and slightly less light, alternating in a pattern that runs for meters and then tens of meters, the pattern repeating with the slow insistence of something that was never arbitrary. Those stripes are the Milankovitch clock. Each couplet of bands, one thick, one thin, represents roughly 1,000 years of time. Each one marks the passage of a full precession cycle over the long Mediterranean summer of the Messinian. The light-coloured bands are the halite, the rock salt that precipitated when the concentration was at its highest, when the water was most reduced, most saline, most committed to its transformation into brine and then into solid mineral. The slightly different bands represent the intervals between when conditions relaxed fractionally. And all of this is there to touch. If you put your hand against the wall of the Rhone mine, you are touching time that is 5 to 6 million years old, and you are touching it in the medium that it used to record itself. Salt, the actual substance of the vanished sea. Not a representation of it, not a model of it, not a diagram. The thing itself, pressed into rock by the weight of subsequent geology and the slow lithification of sediment, but still recognizably what it was at the moment of its formation. the mineral that precipitated when the Mediterranean concentrated itself beyond the point of sustaining its own chemistry. Real Monte is not the only place where the Messinian evaporites emerge from the earth. There are several, distributed around the margins of the old basin, lifted to the surface by the same tectonic forces that have spent the last several million years folding and deforming the crust of the central Mediterranean region. In southeastern Spain, in the province of Almeria, the Sorbus Basin preserves gypsum outcrops that geologists have studied extensively. The Sorbus Basin is a dry, semi-arid landscape now, inland from the coast, eroded by seasonal rivers into a terrain of pale badlands, an appropriate landscape, in a way, for sediment that formed during a period of extreme aridity. The gypsum here is exposed in outcrop across wide areas, the white mineral crusting hillsides and filling the roots of eroded valleys. And nearby, the Niger Basin holds similar deposits. You can walk through these landscapes and pick up pieces of the evaporate sequence, examine the crystal structure of gypsum that formed on the floor of a concentrated Messinian sea, hold in your hand a piece of the crisis as a physical object. On Cyprus, the chalky hills of the Troodos foothills include evaporate deposits from the Messinian. The island's geological history carrying within it this record of a basin in extremis. In the northern Apennines of Italy, the mountains that run down the spine of the peninsula and were deformed by the same collision of Africa and Eurasia that closed the western gateways, Messinian evaporates are exposed in a scattered series of outcrops that mark the locations where the old seafloor has been tilted, folded, and pushed up into the range we see today. The Caltanissetta Basin in central Sicily is another repository of the crisis, a geographic depression in the interior of the island that has preserved a thick sequence of evaporate sediment. All of these places, Spain, Sicily, Cyprus, the Italian peninsula, are pieces of a puzzle that was once a continuous layer beneath a connected sea. The salt giant, as geologists have taken to calling the total evaporate body buried beneath the Mediterranean basin, represents in aggregate something on the order of 1 million cubic kilometers of mineral material. 1 million cubic kilometers. It helps to put that number in some kind of spatial context, although the honest answer is that there is no easily graspable equivalent. It is a mass of salt and gypsum and anhydrite and associated evaporate minerals that, if somehow extracted from the crust and piled together, would form a body the size of a small continent, or rather of a very deep small continent, because the burial depth in the central basins reaches up to 2 and sometimes approaching 3 kilometers below the modern seafloor. 2 to 3 kilometers of salt. Sitting beneath the water you sail across, in every crossing between the ports and cities of the modern Mediterranean world. Sitting beneath the ferry routes and the shipping lanes and the recreational passages of the sailing season and the flight paths of aircraft crossing at altitude. Sitting beneath everything, inert and dense and patient. A record of 5 or 6 million years ago compressed into mineral form and stored in the dark of the deep crust, unvisited and unvisitable by any means available to us. The exposed outcrops in Sicily and Spain and the Apennines are the edges of this body, the places where later geology has brought it close enough to the surface to erode and emerge. The bulk of it is inaccessible, and perhaps always will be. But its presence is not in question. The seismic surveys, the imaging of the crust using sound waves generated at the surface and analysed by the patterns of their return, show it clearly as a distinctive acoustic layer beneath the seafloor, a layer with its own characteristic seismic signature, different from the sediments above it and the older rocks below it. It is there in the data. The shape of it is mapped, at least in broad outline. The salt giant is real. And it is a strange thing, to float on a sea that carries beneath it the corpse of an older version of itself. To sail, as people have sailed these waters for 10,000 years of recorded human history, above an entombed layer that represents the very death of the sea you are sailing on and the conditions that preceded its resurrection. Ancient Greek and Roman sailors had no knowledge of this. Medieval Arab geographers, who mapped the Mediterranean with considerable accuracy, had no knowledge of this. The Ottoman merchants and the Venetian traders and the Phoenician navigators before them, all the people for whom the Mediterranean was the centre of the known world, none of them knew that beneath the keel of their vessels lay a sealed record of a time when the vessel would have had nothing to float on, when the basin was not water but mineral and rock and heat and blistering aridity. We have known it for only a little over 50 years. The Glomar Challenger's cores from 1970 are still within living memory. Now there is one more chapter in the period before the flood, a strange and brief and genuinely puzzling interlude that deserves its own careful attention because it resists the simple narrative of crisis and resolution. It is called the Lago Mer phase, a name that is itself a kind of oxymoron. Lago Mer means, roughly, lake sea, which is an accurate description of a contradiction. Near the end of the Messinian salinity crisis, as the crisis was drawing toward whatever conclusion it was going to have, and the question of what that conclusion was like, whether gradual or catastrophic, is still being argued, something changed in the chemistry of the water within the basin. The evidence for this change comes from the fossil record preserved in the uppermost Messinian sediments, the very last sediments deposited in the basin before the Pliocene transition and the influx of normal Atlantic marine water. In those uppermost sediments, the foraminifera that Maria Biancasita and others had used to track the crisis show something unexpected. The typical marine species, which had disappeared when conditions became too saline and extreme, do not return at the end of the Messinian. Instead, a different community of organisms appears. Small, low-salinity-tolerant crustaceans, specifically ostracods, the tiny bivalved shrimp-like creatures that live in sediment at the water's edge, replace the marine fauna. Among these ostracods, a genus called Cyprideus is particularly characteristic. Cyprideus is not a marine creature in the normal sense. It is a brackish water organism, tolerant of low salinity, the kind of thing you find in estuaries and coastal lagoons and inland seas with reduced salt content. The kind of thing that lives in water that is considerably fresher than the ocean. So the terminal Messinian basin, the basin in its last phase, before whatever brought the crisis to its end, was not hypersaline. It was actually less salty than normal seawater, not a concentrated brine, but a diluted one, not a dying salt sea, but something stranger, a large, enclosed, brackish body of water lying in the deepest depression of the Western world. Surrounded by the salt it had previously deposited and the eroded landscape it had sculpted, but now holding water of a composition unlike either the normal Mediterranean or the extreme hypersaline basin of the crisis's peak. Where did this water come from? The answer that a significant number of researchers favour is the Paratethys. The Paratethys was a large, ancient brackish sea, a vast inland water body that occupied what is now the northern Black Sea region, the Caspian Basin, and areas extending westward through the Balkans and into Central Europe. The Paratethys was not part of the open ocean. It was a remnant of an older, broader marine connection that had been progressively cut off and landlocked by the same tectonic processes that were rearranging the geography of Europe during the Miocene. And because it was largely cut off from the ocean, its salinity was low, a mixture of river inflow and residual marine water, but not the fully saline composition of an open ocean basin. The hypothesis is that at some point near the end of the Mycenaean, the Paratathes found a connection into the Mediterranean basin, either through river drainage or through a temporary low-level spillway somewhere in the Balkans or the Danube Corridor, and its brackish water began filling the drawn-down Mediterranean basin, or some portion of it. The result would have been a lake sea, an enclosed body of low salinity water sitting in the deepest part of the western landscape, fed from the east by a freshwater-rich source and populated by the kinds of organisms that could tolerate those brackish conditions. This is the Lago Mere, and it is genuinely contested. The evidence for it is real: the Cyprideus ostracods, the sediment chemistry of the uppermost Mycenaean layers, the isotopic signatures of the water in which those sediments were laid down. But the interpretation of that evidence involves questions that remain open. How deep was the Lago Mere? How much of the basin did it fill? Was it a single body of water or a series of disconnected pools in the deeper parts of the western and eastern sub-basins? Did the Paratathes connection deliver enough water to raise the level significantly, or only to freshen the surface of a much-reduced residual body? These questions do not yet have answers that everyone agrees on. What can be said with reasonable confidence is that the final phase of the Mycenaean was not a continuation of the peak crisis. Whatever was happening in those last hundreds of thousands of years before the boundary was different from the hypersaline evaporate factory of the crisis's height. The chemistry had shifted. The organisms had changed. The basin was in some state of transition, not yet restored to its normal marine condition, but no longer committed to the extreme desiccation of the earlier phase. It is a strange twilight condition to contemplate. A lake sea, lying at the bottom of the deepest basin in the Western world, its water mildly brackish, its shores the raw eroded faces of canyon walls cut by rivers that had once chased a sea that had fallen away from them. The salt of the crisis layering the deeper floor beneath it, or perhaps around it, or perhaps partly dissolved into its water, the geometry of it is not clear. The sun above it, the Mycenaean sun, which was already in its last few 100,000 years before the tectonic situation at Gibraltar, would resolve itself into something altogether different. Cyprideus lived in that water, those small crustaceans sifting through the sediment with the undiscriminating persistence of creatures that have been adapting to difficult conditions since long before the Mycenaean and long before the Mediterranean. They left their shells in the mud lithified in time. The lithified sediment was buried by subsequent deposition, and then in some places brought back toward the surface by the ongoing deformation of the Mediterranean borderlands. And now, in those exposed outcrops in Sicily and Spain and the Apennines, those shells are there to be found. Tiny, bivalved, the size of a grain of sand, the fossils of Cyprideis in the uppermost Mycenaean layers, telling the story of a strange interlude that the sea passed through in its last chapter before something changed. What changed, how it changed, and how fast is a question that the next chapter of the science must address. And it is the question that carries the most debate, the most argument, the most sharply opposed interpretations among the geologists and oceanographers who have spent their careers on this problem. The transition from the Lago Mare to the fully restored open marine Mediterranean of the Pliocene is not just a chapter in the history of one sea. It is one of the most dramatic geological transitions that can be recognized in the Cenozoic record. And the mechanism of that transition, the how of the sea's return, is where the science becomes genuinely uncertain in ways that are important to hold honestly. But hold that question for a moment longer. Let the Lago Mare have its space first. There is something particular about it that deserves to sit with you in the quiet. Here is a body of water, enclosed, mildly saline, unknown in area and unknown in depth, occupying a depression that was already among the deepest landforms on the planet at that time. A basin that had, in its extreme phase, been a salt desert perhaps 1.5 kilometers below the level of the surrounding ocean. And into this basin, by whatever route, water had returned. Not the right water, not yet, not the open Atlantic water that would eventually restore the Mediterranean to the sea we know, but water. Something moving, something hosting life, something reflecting the sky. It is not difficult to imagine the Lago Mare as a kind of waiting, a pause before the resolution. The basin had been in crisis for what, by human reckoning, amounts to an incomprehensible span of time. Hundreds of thousands of years of evaporation and mineral precipitation and the draining away of all the normal marine life that had once populated the Miocene Mediterranean. And now, at the end of all that, a different kind of water occupying the floor of the old catastrophe. And in it, small creatures going about their lives with the untroubled efficiency of organisms that do not know they are living through the last chapter of something. Cyprides did not know. How could it? It was, as all living things are, entirely present in its own moment. The geological transition that it was recording in the chemistry of its shell was not something it experienced as a transition. It experienced the water it was in. That is all. And the water was there, and it was a particular kind of water, and the Cyprides was adapted to exactly that kind of water, and so it lived. The shells accumulated in the sediment preserved the shells preserved the chemistry preserved the record. And we, much later, read the record. There is something that feels almost unbearably patient about this chain of preservation. The way that the information travels, from the Miocene Ocean's chemistry through the mineral compositions of a tiny crustacean's shell, through the lithification of sediment, through millions of years of burial, through the gradual and ongoing deformation of the Mediterranean borderlands that brings old rock toward the surface, through the erosion that exposes it, through the work of field geologists who recognize it and collect it, through the laboratory analyses that extract its chemical signal, through the papers and debates and revisions of scientific literature, the way that information travels that entire chain and arrives in the mind of someone sitting in a warm room in the 21st century is, if you let it, astonishing. Not dramatic. That is the wrong word for it, or at least an incomplete one. It is not the kind of astonishing that raises the pulse, it is the kind that lowers it. The kind that makes the room feel different, slightly larger, slightly older, slightly more continuous with a world that extends behind it in time for stretches that the ordinary imagination cannot really hold, but can, in certain states. Gesture toward. A gesture is enough. A sense of the scale, arriving not as anxiety but as something more like the physical sensation of depth. Depth is what the Lago Mare offers, held gently and without insistence in the darkness of a drawn-down basin 5.5 million years old. The science is still working on it. The exact extent of the Lago Mare, the precise source of its water, the degree to which it filled the basin versus merely thinly covering its floors, these are research questions with papers still being written, with datasets still being analysed, with debates still being had at the margins of geological conferences. This is, as was said at the outset, living science. Not the settled and finished kind. The kind where the uncertainty is part of the honest account, not a deficiency in the account. And that honesty is its own kind of reassurance, because it means the story is not tidied up beyond what the evidence supports. It means that what is known because it has been tested by cores pulled from the seafloor, by chemical analysis of fossil shells, by the patient comparison of sediment bands to astronomical calculations, by the reading of crystal structures in salt mines in Sicily and exposed hillsides in southern Spain. The story is not a convenience, it is what the rock says, translated by people who have spent their working lives learning how to listen. The Lago Mare is real. Cypridis was there. The Paratethys may have sent water westward through some route that has not yet been identified with certainty. And then, at some point that the sedimentary record marks with a boundary almost as sharp as the one that Maria Biancasita found in the cores from the Glomar Challenger, something changed the situation fundamentally. The closed gate at the western end of the basin, the one that had been closed by the convergence of Africa and Eurasia and had held for the duration of the crisis, did not hold forever. Africa was still moving north. But rock is not a perfect seal, and the landscape of the Gibraltar region was being shaped by forces that combined tectonic deformation with the hydraulic pressure of the Atlantic Ocean, which was sitting above the level of the collapsed Mediterranean basin by over a kilometer, and which was, in whatever geological sense one can attribute intention or pressure to a body of water, present at the door. What happened next is the part of the story that carries the most force, the part that the geological record describes with a kind of economy, a thin boundary, a sharp chemical change, a sudden reappearance of normal marine foraminifera that belies the violence it represents, or what may have been violence. The question of what the return looked like, how fast it happened, what the refilling of the Mediterranean actually was, is the question that divides researchers most sharply. But that question belongs to the last chapter of the story. For now, let the Lago Mare hold its place. Let the Cyprideas rest in their brackish water. Let the walls of the Relmonti mine stand in their striped silence, banded by the precession cycle, counting out their 21,000-year intervals in salt. Let the gypsum outcrops of the Sorbas Basin lie in their pale semi-arid hills under the Andalusian sky, unvisited tonight, white against the darker earth, patient. The salt has been waiting 5.5 million years. It will wait a little longer. And then it came back. Not all at once. Not perhaps in the way that the dramatic imagination prefers, a single cataclysmic instant, a wall of blue Atlantic water crashing down from some high ledge into a dust bowl, the way a dam breaks or a wave overwhelms a seawall. The reality, as researchers have come to model it, may have been stranger than that, and in some ways more frightening for being stranger. More frightening because it was not a discrete event, but a process that accelerated, that fed itself, that began in a trickle and became, over what may have been a very short time by any geological measure, something that no feature of the present world offers an adequate comparison to. But begin at the beginning of it, which is to say at the beginning of what we know, and what we know begins not with the water, but with the wall it was pressing against. The Gibraltar region, in the late Mycenaean, was not the open strait it is today. The strait, as we understand it, that narrow corridor of water between Spain and Morocco, roughly 14 kilometers wide at its narrowest, that connects the Atlantic to the Mediterranean, did not exist in that form during the crisis. What existed instead was a landscape of rock and accumulated sediment and ongoing tectonic deformation, a region being squeezed and rearranged by the same broad convergence of the African and Eurasian plates that had sealed the Betic Corridor in southern Spain and the Rifian Corridor in northern Morocco in the first place. Africa was still moving. The Atlantic was still there, sitting to the west at its normal level, which was more than a kilometer above the collapsed floor of the Mediterranean basin. And the barrier between them was not a clean cliff or a rigid wall, but a complex, graduated threshold. A sill, geologists call it, borrowing the word from architecture, the raised edge at the bottom of a doorway, across which water could not pass unless it rose above a certain height, or unless the sill itself subsided, or unless the flow that managed to get across was vigorous enough to begin carving the sill away. At some point around 5.332 million years ago, something changed at that threshold. The change left a signal in the geological record that is, by the standards of deep time, almost brutally abrupt. Below the boundary, the chemistry and microfossils of the sediment speak of hypersaline water or lagomere conditions, or the various difficult environments of the late Mycenaean crisis. Above it, just above it, in the sediment immediately overlying that boundary, the record shifts to normal open marine conditions. Foraminifera, the microscopic shells of plankton that live only in ordinary seawater at roughly normal oceanic salinity, reappear. The chemical signals of the salt and the brackish water are replaced by the signals of a healthy, connected, Atlantic-linked sea. And this transition, in many cores and outcrops that have been examined, takes place across a layer that represents, by any reasonable interpretation of accumulation rates, a very short time. Not millions of years, not hundreds of thousands, something much shorter. This is where the work of Daniel Garcia Castellanos and his colleagues enters the story. In a study published in the journal Nature in 2009, Garcia Castellanos and his team set out to model what would actually happen if Atlantic water began to flow across the Gibraltar sill. Not to assume a flood and describe it, but to ask, given the geometry of the sill, given the height difference between the Atlantic and the collapsed Mediterranean basin, given the erodibility of the rock and sediment that the water would flow across, what does the physics of the situation produce? What the physics produced was not a waterfall. This is worth pausing on, because the image of a Gibraltar waterfall, water pouring vertically off a ledge into a dry basin below, has become one of the standard illustrations of the Zanclean flood in popular accounts. And it is, in an important sense, wrong, or at least misleading, in a way that changes the character of the event. A vertical waterfall implies a fixed edge, a permanent lip over which water drops. But a sill of rock and sediment, once water begins to flow across it, does not stay fixed. It erodes. The flowing water carries sediment away. The channel gets deeper, and as the channel gets deeper, the head difference between the Atlantic water upstream and the Mediterranean basin downstream increases, which means the flow gets faster, which means the erosion gets faster, which means the channel gets deeper still. This is a feedback loop, and feedback loops of this kind, in geological contexts, are capable of spectacular acceleration. In the Garcia Castellanos model, the initial flow across the Gibraltar sill was modest. Water found a path through subsidence or a crack in the barrier or an existing low point and began to move. But as it moved, it calved. The channel that it travelled was something on the order of 200 kilometres long, sloping downward from the Atlantic level to the lowered floor of the Mediterranean basin, and as erosion cut the channel deeper, the slope and the volume of water crossing it both increased. This was not a waterfall, it was a ramp, a descending rapid of continental scale, growing steeper and wider and more violent as the hours and days and perhaps years passed. The numbers that the model produces at peak conditions are not easy to hold in the mind, and this is not false modesty. They genuinely exceed anything the inhabited world contains a working analogy for. Peak discharge on the order of 100 million cubic meters of water per second. To give that figure a companion, the Amazon River, which carries more water to the sea than any other river on Earth, flows at something around 200,000 cubic meters per second in flood. The flow through the Garcia Castellanos model's Gibraltar Channel at its peak was, by those numbers, on the order of 1,000 times the Amazon. Not 10 times, not 100 times, 1,000. Under those conditions, the model suggests that the water level in the Mediterranean basin could have been rising by more than 10 meters per day. 10 meters. Every day. Think of a 10-story building. Now imagine the water rising 1 floor per day, day after day, the basin filling from the floor, which lay 1.5 kilometers below the level of the surrounding world ocean, up toward the surface, the salt plains and the desiccated sediment, and whatever life had managed to persist in the Lago Mare phase, now buried under water that arrived not in a gentle tide, but in a flood of a scale that the present world does not offer a ready image for. By the model's estimates, something on the order of 90% of the Mediterranean basin could have refilled within a period measured not in millions of years, not in hundreds of thousands, but in something between a few months and a couple of years. This is, on the time scale of geology, the equivalent of an eye blink. A sea, a body of water roughly the size of the Mediterranean, not trickling back in over some long and gradual reconnection, but returning, in the model at least, in something approaching a single overwhelming event. The Zanclean flood. The name taken, as Messinian was, from a Sicilian place, Zancle, an ancient name for Messina. Sitting on the shore of the strait where Sicily reaches toward Italy, where the water coming from the west would have poured next into the eastern basin. And there is physical evidence for that. Not just the chemical shift in the sediment cores and the return of the foraminifera, but something buried in the rock of the seafloor between Sicily and the Maltese escarpment. A large body of sediment and eroded material, imaged by marine geophysical surveys, that a number of researchers, including Milankovitch and colleagues in work published around 2018, have interpreted as the deposits left behind when the incoming floodwaters crossed the Sicily sill and cascaded from the western Mediterranean basin into the eastern one. The architecture of the seafloor in that region, the distribution and character of the buried material, is consistent with what you would expect if an enormous volume of fast-moving water crossed that sill and dropped its sediment load on the far side. It is not proof, in the way that a signed document is proof. Geological evidence rarely is. But it is physical matter, still there in the rock beneath the sea, that speaks to what may have moved through the gap between Sicily and Malta at the end of the Messinian salinity crisis. The debate about exactly what the refilling looked like has not settled, and it is worth honouring that fact rather than papering over it. The catastrophic Zanclean model, the 100 million cubic meters per second, the 10 meters of sea level rise per day, the few months to a couple of years, is influential and widely discussed. And the 2009 Nature paper by Garcia Castellanos and his colleagues has been important in shaping how geologists and geophysicists think about the refilling event. But it is a model. It is a physically grounded and carefully constructed model, but it depends on assumptions about the geometry of the sill, the erodibility of the material, the starting conditions in the basin. Other researchers have argued for a more gradual reconnection, a slower process in which the barrier thinned and Atlantic water seeped in over a longer period before the catastrophic phase, if there was one. The sediment record at the boundary is abrupt, yes, but abrupt in the geological record can still mean thousands of years, or tens of thousands rather than months. What the record does not support, on any serious reading, is the idea that nothing dramatic happened. Something ended the crisis, and it ended it in a way that left a very sharp mark. The salt stopped, the foraminifera returned. The Mediterranean became, within whatever time that boundary represents, a sea again. How the water arrived, at what speed, in what sequence. These remain questions that living researchers are working on, and the answers they are working toward are more detailed and more contested than any single documentary or popular account tends to convey. Hold that uncertainty as the gift it is. The question is still open because the evidence is still being gathered, and the evidence is still being gathered because the event was real and enormous and left traces that can still be read in cores and outcrops and in the buried architecture of the seafloor. The Zanclean stage, which takes its name from that Sicilian place and marks the first age of the Pliocene epoch, begins at approximately 5.332 million years ago. This date, around 5.332 million years before the present, is the Miocene-Pliocene boundary, one of the formal divisions in Earth's geological calendar. Below it in the record lies the Messinian, above it lies the Pliocene, the Zanclean, the world of normal marine conditions, the world of a reconnected Mediterranean sitting in what is now recognizable as its modern relationship to the Atlantic. The crisis ended at that boundary. The flood, or whatever process the return actually was, defines the line. And there is one more thread to follow before the story settles into its close, because it leads somewhere unexpected, somewhere that changes the scale of what the Messinian salinity crisis was, from a regional event in one landlocked sea to something with a reach that extended, quite literally, to every ocean on the planet. When the Mediterranean was cut off from the Atlantic and began to evaporate, the salt that was dissolved in its water did not disappear. Salt does not evaporate. Water evaporates. Salt stays. And so as the Mediterranean dried, whether fully to a desert floor or to a deep hypersaline brine, the salt that had been dissolved in its water precipitated out, settling in layers on the floor of the basin. Carbonates first, then gypsum, then anhydrite, then halite, then the most soluble potash and bittern salts last. All of that mineral mass had to come from somewhere, and it came from the dissolved load of the Mediterranean's water, which had in turn come from the Atlantic during the long period when the Mediterranean and the Atlantic were in contact. The total volume of evaporite that accumulated during the Messinian salinity crisis, the salt giant, the body of gypsum and halite lying buried under the modern seafloor, reaching thicknesses of up to 2 or 3 kilometers in the deep central basins, is on the order of 1 million cubic kilometers. 1 million. To try to give that a spatial companion, it is a body of crystallized mineral comparable in volume to a small continent's worth of mountain range, pressed flat and buried under the sea. That salt was not in the world ocean during the crisis. It had been removed from the water and laid down in solid form in the Mediterranean basin, locked away out of circulation. And this means that during the Messinian salinity crisis, the rest of the world's oceans, the Atlantic, the Pacific, the Indian Ocean, the Arctic, and the Southern, contained all the salt that the global ocean normally contains, minus the portion that the Mediterranean had withdrawn. The total volume of the world ocean is large, approximately 1.35 billion cubic kilometers of water. But 1 million cubic kilometers of salt removed from that system is not negligible, by estimates that have been worked out by researchers studying the crisis. The average salinity of the global ocean dropped by something on the order of 6% during the period when the Mediterranean was locked and its salt was accumulating in the basin. 6%. Every ocean on Earth, measurably, detectably, was slightly fresher during the Messinian salinity crisis than it was before or after. The deep waters of the Pacific, thousands of kilometers from the nearest point of the Mediterranean, carried a different salt concentration because a sea in what is now southern Europe had closed its door and kept its mineral wealth to itself. A Mediterranean event, tectonic, regional. The collision of two plates squeezing shut two corridors in Spain and Morocco left a fingerprint in the chemistry of water on the other side of the planet. And when the Zanclean flood came, or when the refilling of whatever kind it was proceeded to completion, and the Mediterranean reconnected to the Atlantic, and the water rose again above the evaporate deposits, and the basin filled back to something resembling its modern depth, the salt that had been precipitated in the crisis was buried under that new water and new sediment. It has been there since. Roughly 5.5 million years of sedimentation has accumulated on top of it, pressing it down, sometimes deforming it. Salt is not rigid under pressure, and the weight of overlying sediment causes thick salt bodies to flow plastically over geological time, forming domes and ridges and intrusions that complicate the structure of the seafloor above. But the salt itself has not dissolved. The water above it is saline enough that the halite does not dissolve back into the sea. It remains. It is there now, under the blue water and the shipping lanes and the anchoring points of undersea cables, under the sediment columns that oceanographers drill into for their cores, under the fishing grounds and the ferry routes, and the places where you would sit on the deck of a boat at night and watch the stars reflect off the surface and have no way of knowing from the surface that 2 or 3 kilometers below your feet there is a mineral layer the size of a small continent, placed there by the drying of the sea you are sailing on. That is the salt giant. And it is still there. There are 2 questions that this story has carried since its beginning, 2 threads left deliberately open, and it is right to bring them here to the close of the telling, rather than to resolve them with more certainty than the evidence permits. The first question is whether the deep floor of the Mediterranean during the crisis was truly a desert, a baking, sunlit expanse of salt crust and dry sediment lying in hyper-arid air, comparable to the Danakil Depression in the way that a canyon is comparable to a scratch, or whether it was something less absolute than that. A deep, hidden brine lake, perhaps, a body of hypersaline water so dense and so buried below the level of the surrounding world that it was effectively isolated, without the circulation and the life and the chemistry of a normal sea, but still liquid, still wet. Researchers who have examined the evaporate sequences and the sediment record have argued both positions, and the evidence does not resolve cleanly to one answer. There are parts of the record that look more consistent with deep desiccation. There are parts that suggest the presence of water at some depth throughout the crisis. The honest statement is that both models, the deep basin desiccated model and the deep brine lake model, remain alive in the literature, and that the Messinian salinity crisis has not yet given up this particular secret to the satisfaction of all the people who are trying to read it. The second question is whether the return of the sea was the catastrophe that the Garcia Castellanos model implies, or something more gradual. Whether the barrier at Gibraltar failed suddenly, producing the accelerating flood and the 10 meters of sea level rise per day and the refilling in months, or whether it failed slowly, in stages, with water entering and pooling and the level rising and the barrier eroding more gradually over perhaps thousands of years before the basin reached its modern depth. The sediment record at the Miocene-Pliocene boundary is abrupt, but abrupt, as mentioned, is a relative term in the geological timescale, and the debate continues. And these two open questions, was the floor dry or wet, did the water return in an instant or by degrees, are not failures of science. They are the natural condition of inquiry into events that happened nearly 6 million years ago. Events whose physical traces have been compressed and buried and partially erased by the weight of subsequent time. The fact that the traces are there at all, that we can look at a core of gypsum pulled from the deep Mediterranean floor, or at the banded walls of the Rhone mine, or at the buried canyon beneath Cairo, and from those things reconstruct an outline of what the basin went through, is itself the thing worth pausing on. We know what we know because people looked carefully. Because a drilling ship called the Glomar Challenger went out in 1970 and lowered a drill string more than 3 kilometers to the seafloor and pulled up cores that contained gypsum and anhydrite, minerals that cannot form under normal marine conditions, minerals that form only when water evaporates, from the deep floor of an ocean that was supposedly 2 miles deep. Because Kenneth H's and William Ryan and Maria Biancasita and the other scientists on that leg of the deep-sea drilling project looked at those cores and understood what they were reading. Because geologists walked the hills of the Sorbus Basin in Spain and the Caltanissetta Basin in Sicily and the northern Apennines, and recognized in the white and cream and pale layered rock exposed at the surface the same evaporate minerals that the drill cores showed buried far below. Because people measured the precession cycles written in the gypsum bands and matched them to the rhythm of the Earth's wobble, and counted backwards, and found that the crisis lasted on the order of 600,000 years, and ended, as precisely as the tools allow, at around 5.332 million years before the present. Because, in short, the story of what the Mediterranean did in the late Miocene is not a story told by the sea itself or by the time in which it happened. It is a story told by the people who figured it out over decades, by reading the evidence that was left behind and building interpretations piece by piece and arguing about them and refining them and continuing to argue, in the productive way that science continues to argue when the question is genuinely hard and the stakes of getting it right. For understanding ocean chemistry, for understanding how tectonics shapes climate, for understanding what happens when a major ocean connection closes or reopens, are genuinely high. And what the story leaves the listener with, at the end of it, is something that is perhaps not satisfying in the way that a solved mystery is satisfying, but satisfying in a different way. The way that standing at the edge of something very large and very old is satisfying. The Mediterranean is there. It has been there, in various forms, for much longer than the Messinian crisis, and it will be there in various forms for much longer than any of us. But it is not simply there, in the neutral sense that a piece of furniture is simply there. It is there as the result of a sequence of events, a gateway closing, a basin emptying, salt accumulating in layers across the deep floor, rivers cutting into canyons as they chased the fallen base level, a drill ship pulling up desert minerals from the bottom of the sea, the Atlantic pressing at the door until the door gave way, water returning in what may have been the most violent inundation of a single basin in the history of the earth, or in what may have been a slower and more complicated reunion that can be traced and dated and touched on land in the walls of a salt mine and imagined downward from the deck of any ship crossing the sea on a calm night. The salt is still there. The buried canyons are still there, filled with sediment running beneath Cairo and beneath the Rhone Valley, testimony to the rivers that cut through them to reach a sea that had fallen away. The flood scar, or what appears to be one, is buried under the seafloor between Sicily and Malta, in the sediment between one basin and the next. The Miocene-Pliocene boundary sits in the cores and in the outcrops at precisely the point where the crisis ends and the sea begins again, a thin line in the record that represents, in whatever form the refilling took, the moment the Mediterranean stopped being what it was during the crisis and started being, again, something like itself. 5.332 million years ago, the sea came back, and it has been back ever since, and the world's other oceans have carried their slightly higher salinity in the 5.5 million years since the Mediterranean salt returned to circulation, and the foraminifera have been raining their shells down onto the floor in the steady, quiet accumulation that they have maintained through every human civilization and before it, covering the evaporate layer a centimetre at a time, burying the record of the vanished sea under the record of the returned one. You are, if you are anywhere near the Mediterranean tonight, or if you have ever been near it, or if you have seen a picture of it, or crossed it, or eaten fish that came from it, within some degree of connection to a body of water that has done something that very few things in geology are known to have done on quite this scale. It died. It came back. The evidence of both events, the death and the resurrection, is still physically present. In the rock and the sediment and the buried salt and the canyon floors that no river currently touches. Not in any metaphorical or theoretical sense. The material is there. The material is recoverable. The material is, in some cases, walkable. You can go to the Sorbus Basin in Spain on an ordinary afternoon and stand in front of gypsum outcrops that formed at the bottom of the Messinian Mediterranean as it was drying, and put your hand on the rock, and feel a surface that was deposited in a world that no longer exists and has not existed for nearly 6 million years. That the world can do this, can vanish and return, and leave the evidence of both in a form that patient inquiry can eventually read, is not a simple thing. It requires a particular alignment of conditions, an isolated basin, a tectonic gateway, an evaporation rate that outpaces any river or rainfall, time enough for the chemistry to run its course through its layered sequence of minerals. And then, eventually, the failure of the barrier and the return of the water and the burial of the evaporate record under the new sea's sediment. It requires also millions of years of preservation and the right coincidence of later tectonics to bring some of the evaporates back to the surface where they could be found and identified and understood. And it requires people who looked. All of those things happened. The Mediterranean is there because all of those things happened, and because the last of them, the looking, is still happening in the universities and research institutes and aboard the drilling vessels and in the geophysical surveys that are still being conducted over the seafloor between Sicily and Malta and across the deep basins where the salt giant lies buried. The two mysteries: was it truly a desert floor, and did the water return in a violent instant? They remain as open questions being worked on by people who will spend careers trying to answer them, and may or may not answer them completely in those careers, and will leave the remaining uncertainty to the next generation of researchers, who will have better tools and more cores and more geophysical data, and who will carry the questions forward. This is not a failure. This is what it looks like when a science is working correctly on a problem that is genuinely hard at a remove of nearly 6 million years in the sediment of a sea that is still there and that is still, by its simple presence and its chemistry and the structure of its floor, telling the story to anyone who knows how to listen. Let the two questions rest there, unanswered for tonight. The uncertainty is not a hole in the story, it is part of the story. It is the part that says, we do not know everything yet. And the not knowing is not ignorance, but the frontier of what inquiry has so far reached. And the frontier is a good place to settle into sleep, because beyond it is more discovery. And discovery does not require that you be awake to unfold it. It unfolds on its own, in the cores and the sediment and the buried salt, patient as the precession cycle, patient as the 21,000-year wobble of the earth that wrote its tempo into the gypsum bands of the Rhone mine. Somewhere beneath the Mediterranean, the salt is there. Somewhere along the seafloor between Sicily and the Maltese escarpment, the buried sediment of the Zanclean flood rests in the dark. Somewhere beneath Cairo, the Ionile Canyon runs through its sediment fill, the ghost of a river that once cut 300 meters deep through rock to chase a sea that had fallen away. Somewhere in the Sorbas basin, the gypsum is white in the dark, visible only in starlight now, waiting for morning. The sea came back. It came back through a channel 200 kilometers long that was not there before the water made it. It came back at a speed that the instruments of 5 million years later can only model and argue about and refine. It came back and covered the salt and buried the canyons and filled the space where the Lago Mere had held its brackish aliens in their shrinking pool, and the Cyprideis sank into the sediment, and the foraminifera of the open ocean returned to the surface water, and the Mediterranean began again to be the Mediterranean. Not fixed, not permanent, but resilient in the geological sense, which is to say, capable of continuing. You are listening to the story of a sea that was erased and rebuilt, and the evidence of both the erasing and the rebuilding is still present in the rock beneath the water you may tonight be sleeping near, or only imagining. It is one of the stranger truths that the natural world contains, that the ground beneath a sea can remember what it was before the sea returned, and can hold that memory in mineral form, banded by the rhythm of the sky, patient through every subsequent event, for the eventual arrival of the people who would come to read it. This is what the Mediterranean is. Not simply a body of water between continents, a highway for ships, a boundary between climates and cultures. It is a record, it is a document written in salt and gypsum, and the shells of microscopic creatures, and the buried canyons of ancient rivers, and the document says, "This place has been more than one thing, and the sea you see is not the only sea that ever was here. And beneath the surface there is more than the surface shows. The deep thoughts are all there, settled in the sediment. They have been settling for 5.5 million years. They will still be there in the morning. Let the deep thoughts settle, and let yourself sink with them.